This is a simulation of spin 1/2 in an elastic solid. The key points of spin 1/2 is that the center appears to rotate, even though we are inside an elastic solid. You can see this sphere is just placed for visual aid. We can turn it off. So this is actually what spin would look like. But we add the sphere just for visual aid, okay? So I placed this marker here on the sphere so you can see how it appears to rotate. The second point is that the whole configuration repeats after 720 degrees. So not after one rotation, but after two rotations. Let's take a look. It's a little bit hard to see initially. I also placed these green blocks, which should simulate the Dirac belt trick. Now, let's follow this red dot as it goes around. Let's take a starting point. Let's see, next time it's here, let's take a look at the configuration. The belt is on top, the marker is on the left. It goes around one time, and the belt is now at the bottom. It goes around again, and now the belt is back on top. So you can see that it takes 2 turns of the innermost grid points before the entire configuration is back to its original position. When you look a bit from further away, it looks like there is this wave, a transverse wave, going around. And in fact, there is angular momentum. This is the intrinsic angular momentum. So there's nothing really moving around because we are in an elastic solid. You could, in theory, do this in a big pudding if it's reasonably stable, or you could actually do this in your living room if you have rubber bands all over the place. Of course, I'm only showing one plane here, but this is actually a 3-dimensional. So imagine this gigantic elastic solid, and we can add more layers, but it gets a little bit hard to see somewhere I have layers. Oh, here. So I do have more layers. It gets a little hard to see, but it is 3-dimensional. It's not just 2-dimensional. Okay. The other interesting thing is when we place markers, let me place some more markers randomly, different places. What you will observe is that these points, these markers on top. So let's see how we can visualize this best. Let me just reduce this winding a little bit because it makes it a bit easier to see. Otherwise, the circles get a little bit too big, okay, and increase the speed a little bit. So what I did, I decreased the winding a little bit, this curvature here, and I'll explain in a minute. You can see that these markers I placed on top, they all move when looking from above, right? They move counterclockwise, okay? But when you flip around the scene and you look from the bottom, they move clockwise. So this is sort of a precession movement. Imagine there was this, a stick here. It seems to wobble like a precession. So this is similar to a magnetic field because you have a magnet. I mean, because you have a north and a south. The winding. So how this is done? So basically, the essential ingredients here are 3 quaternions that I use to transform every point in this scene. Now, quaternions are nothing really complicated. It just means there's a rotation axis and a certain amount of rotation we use. And here we have 2 different rotation axes for spin. We have this, let me just turn off the auto rotate. So we have this, what I call the winding. Actually, this is from Mark Snowswell, and I want to give credit to him. So he helped me understand this. The winding is basically, let me just remove these markers too. There's too many. The winding is how much we curve the elastic solid towards the center. You can see how this, maybe we can look at from different directions. Also from the side, maybe you can see better here. like we like imagine you reach in and you grab a piece of this pudding and you start twisting it, right? A little bit. So, and you can see how this tapers off as we go further away. This could be something like 1 over r or 1 over r squared or something like that. Of course, we have to exclude the center, otherwise we get infinities. So I excluded the size of the sphere. This is one type of, that's one quaternion. The other one, for, let's just pick some kind of winding here. The other one is the phase. This is a time-based quaternion, and you can see the axis here is a different one. So the winding axis was the, depending on which direction we look at, it was this, I think, the z-axis. And the time-based quaternion is the y-axis. Now, when we make the winding small, let's just keep it running now. You can see now it looks a little bit different. When the winding is just small, you just get a precession movement, and that's it. This marker doesn't appear to rotate at all. It just makes a figure 8, okay? You can see actually the double cover here a little bit. As we increase the winding, this marker it still makes a figure 8, but it's a bigger 8. You can see that, right? Now, as we increase this further and further, as we go towards 180 degrees, let me see if I can get it just about approximately right. It's still a double cover, okay? It's still making the figure 8. It's going around twice, but now the loops of the 8, they overlap. And this is now when we have the spin 1/2 configuration. The description has a link to the simulation. There's also a link to the Elastic Universe webpage, where there's a link to another video, a presentation I did on this. And there's also a Unity implementation with C#. It's a little hard to install, but it has more capabilities. Yeah, let me know if you have any questions.